Hello and welcome to this class presented to you by O3 Schools JAMB app. Now, O3 Schools JAMB app is simply an application which you can install on your Android phones, or your Windows laptops. And what it does is that it gives you access to a bunch of features and variety of options which you can use while preparing for your JAMB. For instance, it has the mock exam feature in which you can set your system and it appears just as it would when you're writing the UTME examination. That means for those of you who are not sure how your computer software will look like when writing JAMB, using your O3 Schools JAMB app, you can actually get an accurate picture of that and can try practice writing your exams to see how your score would be. And you can try be able to guess or measure your improvement as you read and get better in the subjects which you should be taking. It also has other features like it has the places where it can advise you on what subjects to take for a particular course or whether different universities offer different courses. And my personal favorite is the feature in which you can try search for questions by topic. That simply means that once you finish reading up a subject or a topic rather in a particular subject, you can just go to the app and search for that topic, such that it will give you all the questions JAMB has set on that topic. And so you can actually read, answer, and be able to know how well prepared you are per topic, not just per subject. So as you begin to finish each topic, you can actually go there, see all the questions, read them up, and actually be able to improve. Now, how do you get your app? You can simply download it, but after downloading, you will need to activate this app. The activation fee costs 2,500 naira only, and it is very simple and easy to do. Simply follow the steps there. There are about 3 different methods of payment. Pick the one suitable for you, and simply proceed to payment. Once you can complete your payment, your app will be activated. You can be 100% sure of that. We do not fail when it comes to that. So that's how it works. And without much ado, let's go over to today's topic. We shall be looking at simple harmonic motion, also popularly known as SHM. Now, in simple harmonic motion, what is going on? In simple harmonic motion, this is simply the motion of an object, or you may call it the periodic to and fro repeating motion of an object, such that its acceleration is always directed towards a fixed point and is proportional to the displacement from that point. One more time, the acceleration is proportional to the displacement from a fixed point, and it is also directed, towards that point. That point is referred to as the equilibrium position. Equilibrium position. Now, the easiest way to describe this pictorially is by using a simple pendulum. This is the natural state of my pendulum. If I was to take it and let it swing or oscillate freely, these are different stages in flight. Now, as my pendulum is swinging to and fro, what's happening? Please note, let's start from here: A, B, C, D, and E. As it is at A, one thing you must please notice that it is not yet moving. So the kinetic energy will be 0, while the potential energy is maximum. So what happens to this? As it is at this point, it always wants to come to this equilibrium point. So the acceleration is directed towards that point and proportional to the displacement from that point. It is facing here and also proportional to how far it is from here. So the farther it is, the more the acceleration, which it means simply that the acceleration is maximum at this point. So A and E have similar properties. So please note, A and E have similar properties, both ends. So what happens? Once this object is free to move, it begins to move this way. The potential energy starts getting converted into kinetic energy until it gets to this point here. At this point, kinetic energy is maximum and potential energy is 0. This is at C. Ke is maximum. Now, what happens when kinetic energy is maximum? That also means that the velocity must be maximum. But now here's the point. Because velocity is maximum, this object wanted to get to this point. So once it gets here, it seems to want to stop. It has gotten to its aim. But at maximum velocity, it's not easy to do so. You have to decelerate first. That means as this body begins to pass here, because it cannot stop instantly, the acceleration begins to tell it, no, come back here. Which means the acceleration is now, instead of acceleration, moving it faster, is now retardation, trying to stop it. So the acceleration will act on it and try and stop it, but doesn't quite succeed until this body passes all the way from here, and it only finally succeeds in stopping him after it has gotten to this point, E. At this point, velocity becomes zero again and the body stops. But once it stops, remember, the acceleration is always facing this equilibrium position, which means instantly it tells it, please come back here, this is where we want you. So again, the body tries to move. The more it moves, the faster it gets until it gets here again. Once it gets here again, it attempts to stop. But again, stopping is not that easy. So it overshoots it until it's able to stop at A. And it keeps on doing that, ideally, forever and ever. Which means, please note, there are three types of vibration. What we call free vibration. It's also known as undamped vibration. Then there is damped vibration, and there's what is now also called forced damped vibration. Now, what are the differences? In free vibration, this object doesn't experience frictional force, so there's nothing going to stop it. That means this pendulum ideally should move forever and ever without stop. But in real life, you'll notice that doesn't happen. You don't have any object oscillating forever. What stops it? Things like air resistance and frictional force. And that's what brings us to damped vibration. In damped vibration, there's a stopping force, which means that my object cannot move forever, but instead gradually begins to slow down, which is what we observe normally in real life. But then we now have forced damped vibration. In forced damped vibration, the aim is to keep it in harmonic motion, just like free vibration, but it does this by applying a periodic force to the object. Think about it kind of like your swing. When you're on a swing, initially you can push yourself off and begin to swing, but eventually you must stop. How do you avoid stopping? By having someone behind you who pushes you every time you get there. By so doing, you actually never end up stopping. Instead, you begin to oscillate over and over again as long as the person keeps on applying that periodic force. Now, at the level for JAMB, we are paying attention only to free vibration and totally neglecting damped and forced damped. We are going to focus on free vibration. Now, before we can do much analysis on free vibration, we must first of all remember certain terms that will get used a lot in this topic. And a lot of these terms have things to do in common with waves. So if you know waves, these terms should not be familiar to you. And if you are to do this before you do waves, when you get to waves, those terms will also not be unfamiliar to you. For example, we have a term known as cycle. We have frequency. We have period. We also have amplitude. Now, what is a cycle? Basically, a cycle is one complete to and fro movement of the oscillating body, which means, please note, a cycle is not the same as a circle, but a cycle can actually be a circle. One more time. There is cycle and then there is circle, the shape. If we have an object moving around in a circular path, when it has gone around once, that is a cycle, yes. But however, it doesn't always have to be going around in a circle to give you a cycle. If I have my oscillation, like we saw of the pendulum, if it starts from here, if it goes this way and comes back, that is also a cycle. If I'm to use a mass, a spring and a loaded mass, for example, if I was to drag this body and release it, it needs to go up and down. When it goes up and down once, that is also a cycle. So one more time, A cycle can be a circle, but a cycle doesn't have to be a circle. Could also be this. So that it has gone round the oscillation path once, we have a complete cycle. Then next we have frequency. Frequency simply measures how many cycles you can complete in 1 second. The number of cycles, or number of cycles rather, over time. And frequency is measured in hertz. Then next we have period. Period is simply the time taken to complete one cycle. Time taken for one cycle, and it is measured in seconds. Now, with a little bit of observation, realize that these two are almost the same, just reciprocals of each other, which means that F equals 1 over period, and period is also equals to 1 over F. Then the last term we're going to look at here, which is amplitude. Amplitude is the maximum displacement of the body performing SHM from its equilibrium position. Like in the case of your pendulum going to the ends, the equilibrium position is this middle. So the maximum displacement from the extreme to this middle gives us the amplitude. It's that simple. It is always the farthest it can go away from the equilibrium position. So these four key concepts are the things we are going to be using a lot in this topic. And now to start off, the first type of analysis we can, or we shall do rather, is the analysis of circular motion. Circular motion. If an object is moving around in a circle, what is going on there? Because it's an easy way to actually analyze our cycle. Now, the first thing you should know is that when we're moving in a circle, we then get angular versions of our normal linear parameters. What do I mean? Normally, object is moving in a straight line. It has velocity, it has displacement, it has time. Now, if I'm moving in a cycle or in a circle, then I'm going to now have an angular version of each of those movements. I'll have angular velocity, then angular displacement is simply angle turned. I'll have angle, but time doesn't have anything to do with space, so time remains time. Therefore, if you remember this, V equals to displacement over time, then the angular version becomes angular velocity represented by a small letter omega equals to the angle turned, which is theta, representing the displacement over time. It's that simple. This is the formula for angular velocity. Now you may say, okay, after angular velocity, what's next? Let's do a bit of imagination and say, so assuming this body is completing one cycle. If the body completes one cycle. Now, before we look at one cycle, we shall have to look at what makes a cycle a circle. A cycle is 360 degrees. But in this topic, we prefer to use the SI unit of angle, which is not degrees, but instead is radian, properly called rad. So we should know that 360 degrees equals to 2 pi radians. So one cycle is something as saying one revolution, 360 degrees, or 2 pi in radians, 2 pi rad. Therefore, I can see that my angular velocity will be equals to, like we said, it's completing one cycle. In one cycle, the angle is 2 pi in radian. And how long does it take you to complete one cycle? If you remember the parameters we said period is the time taken to complete one cycle. And if one cycle is getting completed, then my time must be equals to the period. And this gives us a very important formula that we shall use. However, after knowing this formula, is there something else I could do with the formula? Yes, I could remember that F equals 1 over T. And look at this formula, this is the same thing as saying omega equals to 2 pi times 1 over T. Therefore, I can replace 1 over T by simply saying omega equals to 2 pi F. So you see, these are two of my formulas to solve for angular velocity. Now with this in mind, the next thing was to remember is that What if we want to now get the linear velocity parallel for each of these? I know angular velocity. What if I want to transfer this angular velocity from being angular into being purely linear? Then there's a general formula for it in SHM. The general formula is that V equals to omega square root of a squared minus x squared. And now, before we get to parameters, let's try and just keep in mind how do we get a and x. Let's assume I have a spring on this horizontal ground here, and then there's a body here, and let's call this place the maximum displacement. Therefore, remember, for this spring to work, the spring was here, I must have compressed the spring to a certain point here, and then this is, let's say, the maximum displacement, which means this middle where the spring wants to rest, it's my equilibrium position. So here. Now, how do we measure x? First of all, please note we measure outwards from the equilibrium position. Equilibrium. From here, we measure outwards. That means from here to here is my amplitude. Well, what if it has not got to the amplitude yet? What if it is somewhere here? Then in that case, from here to here is my x. So x represents the displacement from the equilibrium position, how far you have moved from it. So here to here is my x, this is my amplitude. Therefore, the velocity v is simply equal to omega square root of the amplitude squared minus x squared. But that means a couple things for me. That means when x is 0, when x equals to 0, then v must be omega square root of a squared minus 0 squared. 0 squared is 0 obviously, and a squared minus 0 must be a squared. That means that the maximum velocity v max equals to omega square cancel square root a. So this is the general formula for velocity, while the maximum velocity you can get in SHM is always omega times a. That's very, very simple. Then for the velocity to be minimum, simply means, take note, when x is maximum, when x is 0 rather, v is maximum. But when x equals to a, v becomes equals to 0. Because if x is a, that will be a squared minus a squared, which is 0. Square root of 0 is 0 times omega is 0. So this is when it is minimum, when x is a, and it is maximum when x equals 0. That's for velocity. What if I want to get the acceleration? Well then, for acceleration, all I simply need to remember is that the linear acceleration equals to minus omega squared x. Please just note, in SHM, all we have mostly is a lot of formulas. The terminologies are few and far between. Just remember your formulas. So a equals to minus omega squared x. And for this one, I will then notice that a is maximum when x equals to amplitude. That means a will be equals to minus omega squared a. Then obviously, if x becomes 0, a becomes 0. So you notice velocity and acceleration are doing different things. When velocity is maximum, which is x equals to 0, acceleration will be 0. So when velocity is minimum, which is 0, acceleration becomes maximum. And for those of you that may be asking, how do we get this formula? It's because, as we said on the definition, acceleration is proportional to the displacement from the fixed point, and is always directed towards that point. Because it's directed towards that point, hence the minus. Then from here, introduce your constant. The constant was taken as omega squared, and that's how we got that. Very, very, very simple. So these are the few formulas you must know. First off, generally, for any simple harmonic motion problem, no matter the question, you must know this problem. But now there are now some specific problems that can come up. The first one has to do with something we've been mentioning over and over again, which is the simple pendulum. Now, in the simple pendulum, there's a special problem that can come up, and that is What if you have a pendulum, you know the length, and you want to swing it? How many times or how long should it be swinging? What affects how long it takes to swing? What you should know is that the period in harmonic motion for a pendulum, let's note it, for a pendulum, period equals to 2 pi square root of L over G. Please take notes. This is your simple formula affecting the period and the length. Now, this G is supposed to be constant, indicating that because this formula is simply gotten from by saying C squared equals to 4 pi squared L over G. This is from experiments. We simply know that these two are what vary because in a certain location, G is constant. The one we found square root of both sides, we got this. So please take note, as long as G is constant, then the period varies with the length, but not just the period squared. So in a question, if you're comparing just period and length, the formula is going to be T1 squared over T2 squared equals to L1 over L2. Or if you like, in some cases, you can simply put the square in a bracket. T1 over T2 squared equals to L1 over L2. Either one works. So it's only if you are comparing two. If you are comparing in a particular location, period and length, because some questions they will tell you the length is increased or the length is shortened and so on and so forth. That becomes your easy, simple formula. Now, once I have this established for this particular scenario, one more thing must come to mind. I have this right now, but I should remember that angular velocity equals to 2 pi over period. And that if I rewrite this, it seems to have telling me that c equals to 2 pi over angular velocity. Now, this and this seem to look alike. Because, for example, this is something as saying times 1 over angular velocity. T is t, 2 pi is 2 pi. I'm left with the fact that 1 over omega equals square root of L over G. What this simply means that another way to get my angular velocity is by saying square root of G over L. Now, I know some of you may be looking at this and saying the formulas are too many. Well, please note, the formulas you need to remember here are this, and this. Those are the key formulas. Some of them are simply just proofs to tell you how we are going from one to the other. Like I said, there were two things we are looking at, two special scenarios. One is the pendulum. The second one is the loaded spring. And your spring behaves just like a pendulum, but in its case, the formula becomes T equals to 2 pi square root of M over K. That's it. And in this case, that simply tells you that your period depends on the mass. Depending on the mass there, your period depends on that as long as you're using a particular spring. And therefore, just like this, omega will be equal to the square root of K over M. So these are basically some of the things you should be looking at in this topic. There's one last thing, it's very constant in JAMB, but you should know one more thing about harmonic motion, which is the energy. Energy, as you are aware, is getting transformed from potential to kinetic energy. Please note the maximum energy in your system, energy in SHM, is equals to 1 over 2 Ka squared. This K, like the K here, is force constant, while A is your amplitude. And I'd like to assume that all these symbols here are all familiar. We've seen them before. T is period, L is length, G is acceleration due to gravity, and omega is angular velocity, like we know. Now, the last key we should know is something known as resonance. Resonance. Well, what is resonance? Resonance simply occurs when a body vibrating at a frequency forces another body into vibration at its own natural frequency. How does this work? Every single object in the universe has a natural frequency. That means if we are exposed to frequency of that exact value, we too will get set into oscillation once we experience that frequency. But what causes it? Something else has to move at that frequency for us to feel that frequency. So resonance occurs when another object is moving at the natural frequency of yet another object and ends up setting that object into vibration as well. A good example is one we see at times of videos of opera singers breaking glass with their voice. What they're simply doing is matching the frequency of the sound they're producing to the frequency of the glass. When both match, they set the glass to vibration, which breaks it. And way down back to ask this question at times is either in form of diagram or in the form of a question where they tell you soldiers marching on a bridge are advised to break their steps because it's simply so that they can avoid mistakenly getting to the resonance frequency of that bridge. If all the soldiers are marching uniformly across the bridge, then there's every possibility that they might just reach the resonance frequency of that bridge and they end up collapsing the bridge and themselves with it. So instead, they're advised to break their steps. So as one is going down, rather than being in uniform, one is going down, one is going up. So the frequency will never ever truly match the frequency of the bridge. Now I said there were two ways. That's the theoretical way. And the diagram way is slightly more simple. You can simply give you a diagram with several objects and tell you which of them can set another into vibration. It's simply those of equal lengths. Like in this case now, if these two are the ones that are equal, then these two can set each other into resonance, while the others can't because they do not match. So, with these, I believe it is time for us to do what we always do, which is we are going to open our O3 Schools JAMB app and apply all these formulas and knowledge we have gained towards solving past UTME questions. So just to get my phone here and open my O3 Schools JAMB app. And our very first question comes from the year 2019, Model 1, question 41 on our O3 Schools JAMB app. The year is 2019, Model 1, question 41. A body moves in simple harmonic motion between 2 points 20 meters on the straight line joining the points. If the angular speed of the body is 5 rad per second, that's 5 radians per second, we have to calculate its speed when it is 6 meters from the center of motion. Now there are a few things we have to figure out here. Right now I know that this is one equilibrium point or 1 point, and the distance from here to here is 20 meters. And our body is oscillating across this 20 meters. Now what I must know is that if the body is moving this entire distance, then my equilibrium position must be somewhere in the middle, which is going to be half of 20, distance of 10 meters. Therefore, I know that my amplitude is this middle distance, 10 meters. Then I'm being asked to calculate the velocity when it is 6 meters from the center. Now, if this is my center, as my body wants to start moving, it starts from the center and moves either left or right. But let's go right here. It moves rightwards a distance of 6 meters. Therefore, that means x must be 6 meters. So you see how we did the analysis. If this body is moving a total distance of 20 meters, then the amplitude must be half of that because the equilibrium position must be in the center. So that's 10 meters. While we are finding its velocity at a distance or when it is 6 meters from this center. So that is my displacement from center symbolized by the letter x. So I want to find v. And if you recall from the formulas we have for this kind of equation, this is my best formula to apply. V equals to omega square root of a squared minus x squared. And that simply gives me that v equals my omega is 5, square root of a is 10, and x is 6. So that becomes 5 roots 10 squared 100, 6 squared 36. And 100 minus 36 is 64. That becomes 5 times 8, which gives us 40 meters per second. And if I look at my options, that is very obviously option C. So you see, our methods are simple and precise. For our next question, still on an O3 Schools JAMB app, we're now looking at question from the year 2018, Model 3, question 19. In this case, we have been told, determine the period of oscillation of a body executing SHM whose angular velocity is 628 rad per second. We have to determine the period of oscillation. Now, based on what I know, omega and t, I have to ask myself, is there any formula that relates omega and t together? And I should remember that angular velocity is 2 pi over t. See, once I know my formula, I still remember that t must be 2 pi over omega. That becomes 2 times. I was not told what to take pi as in my question. So I could just work with 3.14 all over 628. 2 times 3.14 is 6.28 over 628. And if I divide this, I get 0.01 seconds. And I'm done here. But when I look at my options, I notice my answer is not there. So what could be the problem? Then I can spot my units and realize all my units, instead of just being in seconds, seem to be like this. ms. Now obviously I'm solving for time. So this cannot be meter second. Instead, this must be millisecond. That means they gave me my answers in milliseconds and not seconds. That's why I have to ask myself, how do I convert this my value from seconds to milliseconds? And to do that is very simple. You multiply by 1000. So 0.01 times 1000 gives me 10 milliseconds. And that would be option C. So you see, questions are simple. All you have to do is have a good handle of the many formulas in this topic, and the solving is very simple. Okay, we move on. Let's try a third question. Now, this one comes from the year 2017, Model 2, and the question number is 23 on our O3 Schools JAMB app. So the question goes, a simple pendulum makes 90 oscillations in 1 minute on the Earth's surface. Makes 90 oscillations in 1 minute. And we know already that a minute is 60 seconds. Okay? Then the question goes, the number of oscillations per minute, the number of oscillations per minute which the same pendulum will execute at an altitude where the acceleration due to gravity is 81% of its value on Earth. Now, I'm still going to represent the end of this question by saying acceleration to gravity at a certain altitude is 81%, that is 0.81 of the normal value on Earth, and write that as simply G. So that simply tells me one thing, that my pendulum is the same, but something is altering, and that is acceleration due to gravity. Now, before I go too far, if I look at the question, they're asking me to find number of oscillations per minute. Oscillations per minute. So I could simply tell myself, okay, which of my terms can I relate to acceleration to gravity based on what I have? And then I should be able to remember that period t equals to 2 pi square root of L over G. So you can see there's a relationship between period and G. Bringing that knowledge over here, I can say, let me get my period first here. My period here would be, period as you are aware is time taken to complete one oscillation. So it will be time, 60 seconds, over 90. And that gives 0.67 seconds. So that's my period. And then if you also analyze this carefully, realize that things are changing. I have two different, I'm going to find another period because I have two different values for G. I have the normal G and I have G at this altitude. So to be clear with everything, I will call this one C1 and my normal G G1. So that I want to find T at that altitude. I'm going to be having T1 and G, or rather T1 and TA. Now let's look here at this formula and ask ourselves, can we try a bit of manipulation to get our answer? If we look over here, we realize that 2 pi is a constant, and this square root of L over here is to remain constant as well because it's the same pendulum. It's really changing location. That means the only thing I should be having here is T, a constant, then this square root of G is down. And from this, I should be able to tell that T1 square root of G1 should be equal to TA square root of GA. Because as you can see from here, if I cross multiply, my constant K is T square root of G. That means any T, that's any period, and the square root of its gravity should always come back and give me the same value. So from here, my T1 is 0.67. Then my G1 is normal acceleration to the gravity. But just because I notice that I have a relationship between these two, I can leave G1 like this because I'll be having TA times square root of, instead of GA, I can put in 0.81 G1. And why did I do so? Because I know to get TA, divide both sides by square root of 0.81 G1 divided by square root of 0.81 G1. This cancels out. TA becomes equal to, now this square root of G1 here is affecting both. So if I separate it, I can have 0.67 times square root of G1 over, let's put them under the same square root, over 0.81 G1. This G1 cancels G1. That becomes 0.67 times square root of 1, which is what is left as the numerator, 1. Square root of 0.81 is 0.9. Okay, so cleaning this up so we can have some extra space to solve. We can therefore say that using our calculator, let us find 0.67 times 1 over 0.9. So over 0.9. So CA should be equal to 0.744 seconds. But please, always be careful with what we are asked. What we are asked to find in this case was number of oscillations per minute. This is the time taken to complete one oscillation. That means in this case, TA is this, and then this time should be taken for these oscillations here is 1 minute, which is 60 seconds. We want to find how many oscillations there will be. And as we are aware, the same formula we used here, CA will be equals to time over number of oscillations. That becomes 0.744, 60 over NA. The NA becomes 60 divided by 0.744. And simply pressing that into your calculator, 744 gives you 80.645. Now, if you look at your options, this answer is not quite there, but I'll do a fair bit of approximation, as you can remember here, to get this value. And as such, we're also free to approximate this to the nearest whole number, since my options are all in whole numbers, and that would be 81. That simply means that this body completes 81 oscillations in 1 minute when it is now at this new altitude. So you see, mind you, the question is not complicated. I'm just dragging out the steps here so you can solve it and see the steps carefully. When solving this your exam, you have to obviously endeavor to be faster with this. Okay, for our next question, still using our O3 Schools JAMB app. This one comes from the year 2017, Model 1, question number 30. 2017 Model 1, question 30. So, this is question 4. If the length of a simple pendulum is halved, that means initially I have one pendulum, let's say L1, and then the length is getting halved. So let's say L1 equals to L initially, then L2 equals to half of L1, which is simply L over 2. So when the length gets halved, its frequency is what? Question is, when the length is getting halved, what happens to the frequency? One more time, how do we look at this? We ask ourselves, is there any formula that relates frequency to length? And as you're aware, typically we know that C equals to 2 pi square root of L over G. But we also know that C is 1 over F. Therefore, here is 1 over F. Now in this case, as you are seeing, unlike the previous one where length was constant and G was changing, in this case, we're taking G as constant and L is changing, implying that this is constant, this is constant. I'm left with 1 over F equals to K root L. And if I cross multiply, this gives me that F K root L equals to 1. And because I actually want to see what the constant will be, and that K will be equals to 1 over F root L. And just because I rather solve it linear, I can therefore say that F1 root L1 equals to F2 root L2. Now, one more time, please note, if this was your exam, all you would need to remember is this part. That if you have an equation where the length is changing and you want to see what happens to the frequency, you can simply do this. So you don't have to solve all these parts in every question. You should simply try and remember this, except for those of us who don't like memorizing too many formulas. Then in that case, as long as you are fast, you could still do this in exam conditions. But once I know this is all I need, I can start my question, because we want to know what happens to the frequency. We want to know what happens to F2 in terms of F1. So I can decide to find F2 here and see that therefore F2 must be equals to F1 square root of L1 over L2. That's we divided both sides here by L2. And therefore F2 must be equals to F1. Then in my square roots, L1 is L and L2 is L over 2. So this is L divided by L over 2. Or if you prefer to make this solving much faster, you know that L over 2 must be 0.5 L. So that will go with division of fractions, which may be a little bit longer. Reason why is because I know here L can cancel L. Then F2 becomes equal to 1 over 0.5 is root 2. So root 2 F1. Indicating that my second frequency simply becomes a root 2 factor of the first frequency. So option A says increased by a factor of 2. Wrong. B says decreased by a factor of 2. Wrong. Option C says increased by a factor of root 2. Obviously, it is being multiplied by root 2. So that is my answer. Option C. You see, these are all very simple. Let's proceed. Now we are going to the year 2013. The year now is 2013, and we are looking at question number 5 from 2013. This one says, this should be our fifth question. A simple pendulum of length 0.4 meters has a period of 2 seconds. What is the period of a similar pendulum? Once I'm doing a similar pendulum, then I have to number L1, T1 of length 0.8 meters. So my new length L2 is 0.8 meters. I want to find the period of this new pendulum. Therefore, relationship between T1 and L1. And so in this case, we know that T2 over T1 was the square root of L2 over L1. If you do not know how we go this, all you have to remember is this guy again, 2 pi square root of L over G. And knowing that in this case, we are dealing with T and L. This is constant, this is constant. So T equals to constant root L over root L over root L. So constant is T over root L. That's all. That's how I got that. Therefore, again, memorize this. You can deal with variation in length and period. So my T2 is unknown. My T1 though is 2. Then L2 is 0.8 and L1 is 0.4. So T2 over 2 equals to square root of 0.8 divided by 0.4 is 2. Then if I cross multiply, T2 equals to 2 root 2 seconds. And if I check my options, that is option D. So again, you see, in Simple Harmonic Motion, you just have to know these formulas and your solving will come across quite easily. Okay, our next question is from the year 2009, question number 9. And for this case, there is no solving, it's just the theoretical type. We are given several examples and told number 1, the motion of the tires of a moving car. Number 2, the motion of a loaded test tube oscillating vertically. Number 3, beating of the heart. Number 4, a stone tied to a string and whirled round. And number 5, the motion of the pistons in a gasoline engine. Which of them or which of the above is simple harmonic? Now, for simple harmonic motion, what do you know about it? It must simply be oscillating to and fro, right? And the key thing though, which means it is not always vibratory, is because you have to look at the acceleration, which was in your formula or your definition rather, being proportional and it's always being directed to equilibrium points. So, first off, motion of the tires of the moving car. That is rotational motion. The tires are just way around. That's rotational. Next up, motion of the loaded test tube oscillating vertically. That's vibratory motion. Then beating of the heart. Yes, simple harmonic. Stone tied to a string and whirled round. That's secular. Then motion of the pistons in a gasoline engine. Also simple harmonic and vibratory. Therefore, our answers must be 2, 3, and 5. Because again, the loaded test tube oscillating vertically is going up, down, up, down, up, down. Equivalent position is somewhere here in the middle and it is oscillating. Simple harmonic. Beating of the heart, simple harmonic, in and out. Then pistons on the gasoline engine, basically that. So please note, in most cases, vibratory motion is usually simple harmonic. So my answer here, 2, 3, and 5 must be option B. See? So move on. 2008 question 10. And for this one, there is a bit of calculation. So 2008 question 10 as our 6th solving example. What is the frequency of vibration if the balance wheel of a wristwatch makes 90 revolutions in 25 seconds? This is very easy. Frequency is number of revolutions over time. So simply 90 divided by 25. And if you press that, you should be getting, I know it's 3. Let's confirm the decimal places. 90 divided by 25, 3.608. And that is option what? Option D. See, this one is very, very short and simple. 2008, question 10. And we move on to the year 2007, number 50. In this one, we have a diagram, which we should be able to remember from our explanations, though. Diagram something like this, and this is bulb here. This is Z, this is Y, this is X, and this is W. Question is, where is the speed fastest? Now, if you remember from the explanations, we said that at point W right here, this guy is not moving. So the speed is minimum. The speed here is also minimum. Then right here, the equilibrium position is where you have maximum speed. Equilibrium position, you have maximum velocity. That result, you have maximum Ke. While at these 2 points, W and Z, you're having minimum velocity and as such, maximum potential energy. So your point why nothing is maximum there. You have both potential and kinetic energy. Okay. Next up, 2001 question 9. 2001 question 9. Then you can see the diagram on your screen on your Oscillatory Schools JAMB app. And you're simply being asked in the diagram, which of the simple pendula will resonate with P when set into oscillation. Now please remember, for resonance, they should be having the same frequency. And as you are aware, the frequency depends on the length. And as such, they're simply asking you which of them has the same length as P. And looking at the diagram very simply, you can all see that the only one whose length is the same as P is T. So my answer is simply D. Option D, T. That's all. And if that is clear, we shall take one last question. Just one more simple question on simple harmonic motion, and we shall be able to call it a day on this topic. Okay, this one is from the year 2000, question number 5. Yes, 2000, question number is 5. A simple pendulum has a period of 17 seconds. When the length is shortened by 1.5 meters, again, now I realize I'm comparing. So I must have T1, then T2. The period is 8.5 seconds. Now, however, what about my L1 and L2? At no place in my question was I told what L1 was. So I can put X there if I so desire, or any other letter. But I'm down told that in the second case, the length is shortened. Shortened means something is removed, minus by 1.5, indicating that I take this length from before and I remove 1.5 meters. So it's T1, T2, L1, and L2. And as before, your formula becomes T2 over T1 equals square root of L2 over L1. T2 is 8.5 and T1 is 17. L2 is x minus 1.5 and L1 is x. Okay, if I look here, I realize this can cancel out 1 and 2. So 1 over 2 equals square root of x minus 5 over x. Now, obviously, what's the next thing I can do? I have to remove the square root from this equation. So square both sides. That gives me 1 squared is obviously still 1, and 2 squared is going to be 4. Then this square cancels the square root here. X minus 5 over x. Cross multiply. X times 1, x. 4 times x minus 5. That becomes 4x minus 20. Collect the like terms. X minus 4x equals to minus 20. X minus 4x is minus 3x equals to minus 20 over minus 3 over minus 3. And what does that give me? That'll be 20 over 3, which gives me 6.67 seconds. And now, on getting this answer, oh, by the way, please, we're solving for distance in meters. But if we look at the options, we can realize this is not in our options. What can we do? This is one of those times I've always told you, when you make a mistake, do not panic and rush to start over. You can simply look through your question and easily identify your mistake. Like from here, okay, we have a formula correct. This is x minus 1.5 over x. But then if you take a look at this line, something has gone wrong. 1.5 here and suddenly just 5 here. So you see, easy mistake, easy to identify and easy to fix. Anyway, I see 1.5, or rather, anyway, I see this 5, I have to now go and change it back to the correct value, which is 1.5. And you can see this is where I use 1.5 in my solving. 4 times 5 give me 20. But in reality, it should be 4 times 1.5. And 4 times 1.5 is simply 6, indicating that here should be 6. And here should be 6. And we know that 6 divided by 3 is 2 meters. And that is obviously option B. So as you can see, despite the fact that we made a mistake, it took us less than 15 seconds to correct that mistake. That is what you should do when you find a mistake, rather than panicking and either just guessing any answer or starting over, which will take more time. You can easily find that mistake, trace it, and correct any place you've used that mistake, and you shall easily get your answer. And with that, we've come to an end of this class on simple harmonic motions. So thank you very much for watching. Do subscribe to this channel to get access to more videos, more tutorials on different subjects and different topics, all brought to you by O3 Schools JAMB app. Remember, get your O3 Schools JAMB app, activate, and success will be yours. My name is Athanasius. Thank you very much for watching.